The phase-link recurrent neural network training procedure works as follows. The program first creates a synthetic seismic world inside the computer. A random number of earthquakes is generated within a given time interval. Sometimes none occur, and sometimes many occur close together in time. Each earthquake is assigned a random origin time, a random location, and a random depth within the model Earth. The time gaps between earthquakes are also randomized, so that the network experiences many different temporal patterns. Some earthquakes are deliberately made to overlap in time, while originating in different parts of the seismic network, making the problem intentionally confusing. Next, the program performs simplified earthquake physics to estimate when seismic P waves and S waves would arrive at different seismic stations using a simple Earth velocity model. After the arrivals have been calculated, some peaks are randomly removed so that station coverage varies from one earthquake to another, much like in real seismic networks, where not every station records every phase clearly. During training, the network is shown millions of examples in which the correct grouping is already known, because the synthetic earthquakes were generated by the computer itself. Suppose the synthetic generator creates a training table similar to this. During training, the recurrent neural network may choose P1 as the root pick. The network then attempts to determine which of the surrounding picks belong to the same earthquake as that root pick. Over time, the network gradually learns statistical patterns that tend to indicate a common origin. Importantly, nobody explicitly tells the network any rules. Instead, the network discovers those patterns for itself through repeated exposure to many training examples. For example, it may gradually learn patterns such as pattern 1. If two picks occur at nearby times and their timing matches expected seismic travel time relationships, then they often belong together. Pattern 2. If station A receives a P wave and station B receives a P wave slightly later, and that delay resembles what earthquakes typically produce, then the picks may belong to the same event. Pattern 3. If several stations record arrivals whose relative timing is geometrically consistent, then those arrivals are likely to have originated from the same earthquake. After millions of synthetic earthquakes, the recurrent neural network develops Hernal's sense of what a real earthquake looks like in terms of its seismic picks. Having already encountered millions of similar situations during training, the network can often identify the correct cluster of picks belonging to a single earthquake without ever explicitly solving for the hypercenter first. The desired output then becomes something like this. The key insight is that the network does not necessarily need perfectly realistic earthquakes in order to learn the association problem. It mainly needs to learn the patterns that govern how seismic arrivals relate to one another in time and space. Since the network requires only station locations and seismic arrival times, scientists can simulate enormous numbers of artificial earthquakes and create essentially unlimited training examples. Once it has learned these relationships from simulations, it can then apply that knowledge to real seismic data. This idea is often called sim-to-real learning. First train the system inside a simplified virtual world, and then allow it to operate in the real one. It is somewhat like teaching a pilot in a flight simulator before handing them an actual airplane, considerably safer for everyone involved, including the mountains. By training on millions of these synthetic seismic scenarios, the network gradually learns the characteristic temporal and spatial patterns produced by real earthquakes. In this way, it learns how to handle messy real-world seismic data in a sensible and robust manner. Phase-link approaches the real problem in several steps. First, the system receives a continuous stream of seismic picks. Each pick contains a few basic pieces of information: the location of the seismic station, the time at which the signal arrived, and the type of seismic wave, either a P wave or an S wave. Next, the picks are divided into many overlapping short sequences. Imagine a collection of red P-wave picks, blue S-wave picks, several overlapping earthquakes, and numerous random false or noisy picks. At this stage, the earthquakes have not yet been separated. Each clustered red and blue streak represents arrivals from a single earthquake recorded at many stations. The random isolated dots scattered throughout the plot are mostly false picks or unrelated noise, or perhaps Metallica jamming somewhere nearby. Notice that the red and blue dots tend to form linear trends. Because seismic waves propagate outward from the earthquake source at approximately constant velocities over a limited station network, arrival time plotted against station latitude or longitude appear approximately linear. P-wave arrivals appear earlier. S-wave arrivals appear later for the same station distance. As a result, the red P-wave trends tend to be flatter, while the blue S-wave trends tend to be steeper. Each paired P-wave and S-wave trend typically corresponds to a single earthquake. They may slope either left or right, depending on where the earthquake is located relative to the seismic network. If the earthquake lies north of the stations, then the northern stations are closer to the source, and arrivals occur there first. The streak may therefore tilt in one direction. If the earthquake lies south of the stations, then the southern stations are closer to the source, and arrivals occur there first. In that case, the streak may tilt in the opposite direction. For each sequence, PhaseLink treats the first pick as a root pick. The neural network then asks a simple question about every other pick in the sequence. Does this pick belong to the same earthquake as the root pick? The system must then determine which picks truly belong together as part of a single earthquake. In this way, it gradually builds earthquakes by combining overlapping groups of linked picks. PhaseLink constructs earthquake clusters, that is, coherent families of related arrivals recorded across the seismic network and originating from the same earthquake, step by step from these predictions. If two clusters overlap strongly enough, the algorithm concludes that they likely represent the same earthquake. If two clusters share many of the same picks, they are merged into a single event. The newly formed cluster is then compared with all previously created clusters. This decomposition makes the task far more manageable and allows the method to handle many overlapping earthquakes simultaneously. Looking more closely at the algorithm, as time progresses, different seismic stations blink as they detect arriving seismic waves. For example, at 4.56 seconds, the station located at latitude 33.57 and longitude -116.67 records a P-wave arrival. Shortly afterward, another station records either a P-wave or an S-wave arrival. Then another station does the same, and then another. In this way, the seismic network produces a continuous, time-ordered stream of seismic picks. Each pick contains basic information: the latitude and longitude of the station, the arrival time, and whether the phase is a P-wave or an S-wave. Each pick is represented inside the network using 5 features: the latitude of the station, the longitude of the station, the pick time relative to a reference pick called the root pick, whether the phase is a P-wave or an S-wave, and a final binary indicator specifying whether the entry is a real pick or simply an empty placeholder added for padding. The root pick is simply the first pick, one particular seismic arrival, either a P-wave or an S-wave pick, inside the current sliding window. The window is temporal, spanning at most approximately 120 seconds and containing at most 500 picks. Within that window lies a mixed collection of P-wave and S-wave arrivals. The network then attempts to determine which of those 500 records belong with the first pick. Only one earthquake is identified from a given root pick analysis. Within the window, the network sees a chaotic mixture of P-wave arrivals, S-wave arrivals, arrivals from several overlapping earthquakes, false detections, and noisy picks. By this stage, however, the recurrent neural network has already learned realistic relationships between seismic arrivals during training. It has learned to recognize patterns involving arrival time differences, station geometry, P to S timing relationships, and the overall temporal structure produced by earthquakes. As a result, the network internally evaluates something like, could this pick have been generated by the same earthquake that produced the 4.56-second root pick? The output is probabilistic. A value close to 1 indicates that the pick probably belongs to the same earthquake. A value close to 0 indicates that it is probably unrelated. After making predictions for one window, the system shifts forward by a single pick. The previous second pick now becomes the new root pick, and a new sequence is formed. For example, when the window advances by one pick, the next pick becomes the new root pick and is automatically associated with itself. For this reason, it always receives the binary value 1, regardless of whether it is noise or a genuine earthquake pick. The value 1 in this case simply means this pick belongs to itself. The remaining values in the row are answers to a question that the recurrent neural network resolves automatically. Does this later pick belong to the same earthquake as the root pick? If the answer is no, a value of 0 is assigned. If the answer is yes, a value of 1 is assigned. The procedure continues as the window keeps sliding forward, one pick at a time. Because neighboring windows overlap strongly, the same picks may participate in many different local association tests. Eventually, enough mutually consistent positive associations begin to accumulate that the algorithm identifies a probable earthquake cluster. In the figure, this occurs at the stage where a sufficiently large group of picks repeatedly links together across many overlapping windows, indicating that they most likely originated from the same earthquake. These newly detected clusters are highlighted in yellow. The window then continues sliding through the seismic stream. Whenever additional nearby positive associations are identified, they can either nucleate new clusters or reinforce existing ones. Eventually, all of these overlapping local predictions are aggregated backward through the prediction matrix, producing larger and more coherent groups of picks corresponding to individual earthquakes. Some of these local groups may later merge into even larger clusters if they share enough picks in common, ultimately converging toward the final set of detected earthquakes. Picks that remain unrelated or appear to be noise are discarded. An important point is that PhaseLink accomplishes all of this without actually calculating earthquake locations during the association step. One major advantage of this approach is that it naturally tolerates false picks and noisy seismic data. Another advantage is that it avoids the computationally expensive grid search methods traditionally used for earthquake association. Rather than exhaustively testing possible earthquake locations one by one, the neural network learns the relevant relationships directly from the patterns hidden within the seismic arrivals themselves. Once the picks have been associated into a single earthquake cluster, a separate earthquake location algorithm can then estimate the earthquake hypocenter, the origin time, and therefore the source-to-station distances. Only after that step can a true travel time plot be constructed for either seismic phase, such as the one shown in the final panel. At that stage, every pick has been assigned to a particular earthquake. The earthquake location has been estimated, and the distance between the source and each recording station is known. The arrivals can then be plotted against source-to-station distance, producing the familiar travel time branches for P waves and S waves. Each colored group on the left represents one final earthquake cluster after the association process has been completed. The black picks are arrivals that were rejected as unrelated signals or noise. Within each colored cluster, the picks align in a physically consistent travel time pattern, suggesting that they most likely originated from the same earthquake. For example, the two orange streaks most likely represent the P wave and S wave arrivals generated by a single earthquake. In other words, the orange pair of streaks corresponds to two different wave families produced by the same seismic event. Once the picks have been associated into earthquake clusters, a separate earthquake location algorithm can estimate the hypocenter and origin time of each event. These estimates then allow the source-to-station distance to be calculated for every arrival. It is important to note that this panel is therefore different from the earlier visualization. Here, the horizontal axis represents the actual source-to-station distance. Because distance is always positive, and because larger distances generally correspond to later arrival times, the travel time branches naturally rise toward the right. As a result, the familiar P-wave and S-wave travel time curves emerge as upward-sloping branches, with the faster P-wave arrivals appearing below the slower S-wave arrivals. PhaseLink uses the PyTorch library as its deep learning framework. Historically, TensorFlow dominated many machine learning workflows, whereas modern scientific machine learning often favors PyTorch because of its flexibility and research-oriented design. PyTorch serves as the computational engine that stores the GRU neural network architecture, computes predictions from the seismic PIC data, optimizes model weights during training, handles the required tensor algebra, and performs backpropagation. The GRU, or Gated Recurrent Unit, is a type of recurrent neural network specifically designed for sequential or time-dependent data. In the case of PhaseLink, it learns temporal relationships among seismic arrivals recorded at multiple stations in order to determine which arrivals most likely belong to the same earthquake. From left to right, the workflow begins with the physical information describing the seismic network. The files stationlist.txt, tt.p, and tt.sg contain the station coordinates and the theoretical P-wave and S-wave travel time tables. Together, these files define the geometry of the seismic network and the expected behavior of seismic wave propagation. This information is first used by PhaseLink dataset.py, whose role is to generate synthetic earthquake training examples. Rather than relying exclusively on real earthquakes, the program creates artificial sequences of seismic arrivals that mimic realistic earthquake behavior. From this process, it produces training datasets such as Shimani Train X.npy and Shimani Train Y.npy, along with mapping files including stationmap.pkl and snclmap.pkl. These training datasets are then passed to PhaseLinkTrain.py. At this stage, the GRU neural network is trained using the PyTorch deep learning framework. The network repeatedly examines synthetic arrival patterns and gradually learns which combinations of PICs are likely to belong to the same earthquake. During training, the Adam optimizer adjusts the internal network weights through backpropagation in order to reduce prediction error. The final trained model is then saved within the PhaseLink model directory as files such as model_099_0.016297.pt. Next comes the real association stage, performed by PhaseLink-eval.py. Here, the trained model is applied to the real seismic PIC file, ANSA GPDJ10 REMD output, which contains candidate P-wave and S-wave arrivals detected at many seismic stations. Using the trained GRU model together with the station geometry, travel time metadata, and mapping artifacts, the program determines which PICs most likely originated from the same physical earthquake. Finally, the associated earthquakes are written to the output catalog sjfzdlinked.nloc. This file represents the final linked earthquake catalog, in which many individual P-wave and S-wave arrivals have been grouped into discrete earthquake events. Optionally, PhaseLinkPlot.py can then be used to visualize the results, the trained models, or the association behavior. Files such as PhaseLinkTrain.py and PhaseLinkEval.py explicitly import the PyTorch framework, making PyTorch the computational engine that performs the neural network calculations throughout the workflow. To experiment with the PhaseLink Recurrent Neural Network, or RNN, I used both the synthetic and real datasets provided in the GitHub repository. The synthetic training data are based on the seismic network of Shimane Prefecture in Japan, whereas the real PIC dataset corresponds to the ANSA seismic network in Southern California, primarily within the San Jacinto Fault Zone region. The real dataset consists of seismic phase PICs recorded over 2 consecutive days, Day 001, January 1st, 2018, and Day 002, January 2nd, 2018. These PICs were subsequently associated by PhaseLink into 1,165 candidate earthquake events. Ross et al. 2019 trained the model using 3 NVIDIA GTX 1060 GPUs, the Adam optimization algorithm, Kingma and Barr 2014, and a mini batch size of 96. In contrast, I trained the model on a desktop PC equipped with an AMD Ryzen 7800X 3D processor and 32GB of DDR5 RAM running at 6000 MHz. The software was executed through bash commands within WSL Ubuntu Linux running inside Windows. A Linux scientific computing environment was therefore established through the Windows PowerShell interface, and Python 3.12 was installed directly within the Linux environment. Training was initiated using the command python phaselink train.py and required approximately 8 hours on my system. During training, the GRU network repeatedly examined synthetic earthquake association examples and adjusted its internal weights through backpropagation. The training process was organized into epochs, where each epoch represents one complete pass through the entire synthetic training dataset. After all training examples had been processed once, the network began another epoch and revisited the same examples while progressively refining its internal parameters. This cycle was repeated many times, allowing the model to gradually improve its ability to recognize which seismic arrivals belong to the same earthquake. The real earthquake association stage was then launched using Python phaselink eval.py params JSON. After the neural network had examined all subsequences of PICs, phaselink combined those local predictions into actual earthquake detections. For every subsequence examined by the recurrent neural network, the model produces a prediction table describing which PICs appear to be associated with the root PIC of that subsequence. The phaselink workflow processed approximately 100,000 total GPD triggers, consisting of 67,693 PICs on day 01 and 32,307 PICs on day 02. From these arrivals, phaselink identified 1,165 candidate earthquake events. After the overlapping local predictions were merged into earthquake clusters, each detected event was represented by a collection of associated seismic PICs. For example, event number 29 contains 13 associated seismic PICs. These include both P-wave and S-wave arrivals recorded at multiple seismic stations. Each line in the event listing corresponds to a single seismic arrival that has been assigned to the same inferred earthquake. In other words, the association process has determined that all 13 arrivals are sufficiently consistent in their timing and station geometry to have most likely originated from a single seismic source. The actual seismological interpretation of the deep learning-assisted phase association follows next. At this stage, we can begin transforming the raw detections into meaningful seismological patterns. The figures shown here are custom scientific visualizations generated directly from the phaselink output catalog by executing Linux-based Python scripts from the WSL bash command line environment. It is important to note, however, that earthquake locations have not yet been computed. Phaselink has associated seismic PICs into earthquake clusters, but a separate earthquake location procedure is still required to estimate hypocenters and origin times. Consequently, the analysis is currently limited to visualizations that depend only on the associated PICs themselves, such as PIC distributions, temporal clustering, station participation, association statistics, travel time consistency patterns, and other catalog-level properties. Spatial analyses involving earthquake hypercenters, fault geometry, depth distributions, or seismicity maps must await the subsequent earthquake location stage. For this graph, the horizontal axis represents the epoch number. An epoch corresponds to one complete pass through the entire training dataset. Thus, epoch 1 represents the first learning cycle, whereas epoch 100 represents the 100th learning cycle. The vertical axis represents the validation loss. Validation loss measures how wrong the GRU predictions are when tested on validation data that were not used during training. Lower values indicate better performance, more accurate predictions, and more successful learning of the earthquake association task. In essence, validation loss is a numerical measure of how wrong the neural network is when associating earthquakes on data it has never seen before. At the beginning of training, the loss decreases very rapidly. This indicates that the GRU quickly learned the basic structure of the seismic association problem. In other words, the network rapidly discovered fundamental relationships among arrival times, station geometry, and phase patterns. Later, the curve gradually flattens. This indicates that learning continued, but that each additional epoch produced progressively smaller improvements. Such behavior is characteristic of training convergence. The network had already learned most of the important patterns, and further refinement became increasingly incremental. Overall, this figure demonstrates that the GRU successfully learned a stable and effective earthquake association strategy from the synthetic training data. This figure was generated by running a Python script from the bash command line, python plot ps-struct.py. The script uses the matplotlib visualization library through the graphical environment supported within Linux. The resulting figure is essentially a move-out structure plot showing how P-wave and S-wave arrivals propagate across the seismic network. The horizontal axis represents the geographic latitude of the seismic stations. The vertical axis represents the arrival time relative to the first pick, measured in seconds. Consequently, each vertical column corresponds to one or more stations located near a particular latitude. This type of plot is useful because it allows us to visualize how seismic arrivals spread through the network as a function of both space and time. Notice that the red points tend to cluster lower in the figure, while the blue points extend upward. This behavior is expected because P-waves travel faster than S-waves. As a result, P-wave arrivals generally occur earlier and therefore appear lower on the plot, whereas the slower S-wave arrivals occur later and tend to appear higher. Most importantly, this figure allows a qualitative inspection of whether the associated arrivals behave like physically realistic seismic wave propagation. If the associations produced by PhaseLink were largely incorrect, the arrivals would tend to appear randomly scattered without coherent structure. Instead, the plot reveals organized patterns consistent with expected P-wave and S-wave move-out behavior. Consequently, the figure provides qualitative evidence that the PhaseLink associations are physically plausible and that the resulting catalog preserves meaningful seismic propagation relationships. This figure presents a geographic map of the entire seismic network used throughout the PhaseLink workflow. The densest concentration of stations corresponds to the core Southern California seismic network, where station coverage is particularly high. The map also functions as a station participation intensity plot, illustrating how strongly each station contributed to the final associated earthquake catalog. In this visualization, symbol size scales with participation intensity. Consequently, larger circles indicate stations that contributed a greater number of associated seismic picks, whereas smaller circles indicate stations that participated less frequently. Stations with large symbols therefore played a particularly important role in detecting and associating earthquake arrivals within the catalog. This type of visualization provides a useful overview of network utilization and helps identify which parts of the seismic network contributed most strongly to the earthquake association process. This figure is a temporal detection rate plot, showing how many earthquakes were detected during successive time intervals. Each point represents the number of associated earthquake events occurring within a particular time bin. The purpose of this plot is to investigate the temporal clustering of seismic activity within the PhaseLink catalog. Several features are immediately apparent. At the beginning of the record, the detection rate is relatively high, indicating a period of intense seismic activity. This is followed by a pronounced decline in the number of detected earthquakes over time. Such behavior may reflect several possible seismological processes. For example, it could indicate the presence of an earthquake swarm, in which numerous earthquakes occur within a relatively short time interval. Alternatively, it could represent aftershock decay, where seismic activity gradually decreases following a larger triggering event. Regardless of the precise cause, the figure clearly demonstrates that the detected earthquakes are not distributed uniformly through time. Instead, they exhibit temporal clustering, meaning that earthquakes tend to occur in bursts, separated by quieter periods. The presence of such clustering is an important observation because it is characteristic of many real earthquake sequences. Consequently, the graph provides qualitative evidence that the phase-link catalogue is capturing meaningful temporal patterns rather than producing randomly distributed detections. This figure shows which seismic stations contributed most strongly to the phase-link earthquake catalogue. Participation intensity is measured by the number of associated seismic peaks contributed by each station. Stations with higher values played a larger role in detecting and associating earthquake arrivals, while stations with lower values contributed less frequently. The plot therefore provides a simple overview of how different parts of the seismic network contributed to the final catalogue. This histogram shows the distribution of inter-event times, that is, the time intervals between consecutive associated earthquakes. The horizontal axis represents the time separation between neighboring earthquake detections, while the vertical axis shows how frequently those intervals occur. The distribution is strongly concentrated at small inter-event times. This indicates that many earthquakes occur close together in time, rather than being evenly spaced throughout the catalogue. Such behavior is characteristic of temporally clustered seismicity and suggests the presence of bursts of earthquake activity, such as earthquake swarms or aftershock sequences. Overall, the figure provides additional evidence that the phase-link catalogue captures realistic temporal organization within the seismicity. This histogram shows the distribution of event durations within the associated earthquake catalogue. Here, event duration refers to the time span between the first and last associated arrival assigned to a given earthquake. The distribution is strongly concentrated around approximately 20 seconds. This means that most associated earthquakes generate network-wide arrival sequences spanning roughly 20 seconds. The duration depends primarily on how the earthquake interacts with the seismic network. For example, if an earthquake is relatively small, local, and recorded only by nearby stations, the associated arrivals may span only a few seconds because all recording stations are close to the source and travel time differences are small. In contrast, earthquakes recorded by many stations, including more distant stations, may generate arrival sequences spanning 20 to 40 seconds or more, because distant stations receive arrivals later, particularly the slower S-waves. An interesting feature of the histogram is its approximately Gaussian, or normal-like shape. This is encouraging because the duration of an associated event is influenced by many independent factors acting simultaneously, including earthquake location, station geometry, event size, network aperture, and the mixture of P-wave and S-wave arrivals. In physics and statistics, when many independent factors contribute to an observed quantity, the resulting distribution often tends toward a Gaussian form. Although a normal-like distribution does not prove that the associations are correct, it is consistent with a catalogue generated by physically realistic seismic processes. In practical terms, the figure suggests that the earthquake wave field typically sweeps through the active seismic network in roughly 20 seconds. This provides additional evidence that the phase-link catalogue possesses internally coherent timing structure and that the associated arrivals behave in a physically plausible manner. This plot shows the cumulative number of associated earthquakes through time. The horizontal axis represents time, while the vertical axis represents the cumulative number of detected earthquakes. In other words, each point shows the total number of earthquakes detected up to that moment. This is one of the most important catalogue-level diagnostics in seismology because the slope of the curve directly reflects the earthquake occurrence rate. Steep segments indicate that many earthquakes occurred within a relatively short period of time. Such behavior may reflect swarm activity, aftershock bursts, or other episodes of intense seismic activity. Flatter segments indicate fewer earthquakes and therefore quieter seismic periods. In this catalogue, an initial phase of rapid growth is clearly visible, where the curve rises steeply. Later, the curve progressively flattens, indicating that the earthquake occurrence rate decreased substantially with time. From a physical perspective, this behavior is highly characteristic of clustered seismicity, such as an aftershock sequence or a seismic swarm. The figure therefore provides additional evidence that the phase-link catalogue captures realistic temporal organisation within the detected seismicity.